Pluto, a distant and secretive planet, was once considered part of our local planetary system. However, recent surprising statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have thrust Pluto back into the spotlight. They proposed that this icy world might be on a potential collision course with Neptune. How could this be possible, and what consequences would such a catastrophic event have? Could this be a fascinating cosmic anomaly, or is there something more to this looming disaster? Join us as we delve into the potential outcomes of a Pluto-Neptune collision. Once categorized as a planet and later reclassified as a dwarf planet, Pluto remains a subject of intrigue in the vast cosmos. This is evident from the recent speculations by renowned experts. Pluto's orbit closely intersects with Neptune's, which has raised concerns among astrophysicists, including Neil deGrasse Tyson and Michio Kaku, who warn of a potential disastrous impact between the two, with significant repercussions for Earth. But how could such an event happen? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit. Since its discovery in 1930, Pluto has not even finished a full revolution. Yet, the fascination doesn't end there. Pluto's orbit is exceptionally elliptical, diverging greatly from the nearly circular orbits of the major planets. A more intriguing feature is its tilt, 17 degrees to the ecliptic plane, making its path noticeably tilted compared to the other planets. This inclination and eccentricity introduce additional layers of complexity to its orbit. One of the most remarkable aspects of Pluto's orbit is how it intersects with Neptune's. For about 20 years during each orbit, Pluto comes closer to the Sun than Neptune, defying what one might expect based on their positions in the planetary system. This raises the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational interactions of other planets. The study of Pluto's orbit began immediately after its discovery, as astronomers sought to understand its unique path. Unlike most planets, whose orbits lie close to the ecliptic plane, Pluto's orbit stands out due to its steep inclination and eccentric shape. The mystery deepened as scientists realized that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit, despite these complexities, demonstrates the intricacies of celestial mechanics. The three-body problem in space refers to the challenge of calculating how three objects in space, like Pluto, Neptune, and the Sun, interact with each other gravitationally. This is similar to predicting where objects will move based on their starting positions and mutual gravitational effects. In Pluto's case, the problem shows how its orbit, Neptune's, and the Sun's gravity all interact in a complex manner. Astrophysicists highlight terms like asynchronous libration, orbital precession, and the VZK oscillation to explain this phenomenon. Asynchronous libration refers to how whenever Pluto crosses Neptune's orbit, it is at least 90 degrees away from Neptune. This spatial separation is key to preventing a collision. Orbital precession refers to the slight upward movement of an orbiting body. For Pluto, this means that when it nears Neptune or another large planet, it is positioned above their orbital plane, providing an added protective measure. Another important factor is the VZK oscillation, which describes how Pluto, Neptune, and the Sun's gravitational forces influence each other. This oscillation helps to maintain Pluto's orbit, preventing any erratic movements that could lead to a collision. Despite Pluto's seemingly erratic path, this oscillation stabilizes its movement over long stretches of time, revealing that even chaotic-seeming systems follow hidden patterns and rules. These factors help to keep Pluto's orbit stable, ensuring that it doesn't crash into Neptune or drift too far off its course. The three-body problem is crucial for understanding the changes in these orbits and the interactions between celestial objects. Studying this helps scientists learn more about Pluto, our solar system, and even distant stars and planets. Mathematical simulations in the 1980s revealed that despite these stabilizing effects, Pluto's orbit is unpredictable. Even small variations in its initial conditions could lead to significant changes over millennia. Nevertheless, Pluto's orbit has been found to maintain stability over extremely long time scales. Further investigations have helped us understand how Neptune, Jupiter, and Saturn affect Pluto's orbit, There is a unique relationship between Neptune and Pluto. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. Jupiter's immense gravity also plays a crucial role in stabilizing Pluto's orbit, preventing it from veering too far into Neptune's territory. Saturn's gravitational pull adds another layer of stability. These findings suggest that Jupiter, Saturn, and Neptune are working in tandem to ensure Pluto's safe passage through space without encountering any significant problems. Without these gravitational interactions, the solar system could be a much more chaotic place where objects like Pluto could crash into other planets or be ejected from their orbits, triggering a cascade of events. For Pluto, understanding its orbit is essential, particularly with discussions about the possibility of it colliding with Neptune in the future. This also gives us a clearer understanding of the dynamic nature of the nearby planetary system. The case of Pluto highlights how even the most seemingly unstable orbits can reach a state of equilibrium through the intricate interplay of gravitational forces and orbital mechanics. It also underscores the importance of continuous observation and research to better comprehend our place in the universe. The study of celestial bodies often leads us to confront their strange behaviors, and Pluto's orbit is a prime example of this unusual nature. The concept of orbital chaos, which refers to the sensitivity of a celestial body's orbit to its initial conditions, is clearly demonstrated by Pluto's path. Even slight changes in its position or speed can lead to dramatic shifts in its long-term orbit. Automated simulations have been instrumental in helping researchers understand Pluto's movements in space. These simulations employ sophisticated mathematics to model the gravitational interactions between Pluto, Neptune, and other bodies in the solar system. By tweaking small details in the simulations, scientists can observe how even tiny changes can significantly alter Pluto's trajectory. In the late 1980s, these simulations uncovered fascinating insights about Pluto's orbit. While stabilizing factors like asynchronous libration and orbital precession help maintain stability, Pluto's orbit can still be erratic if its initial conditions vary even slightly. However, despite the apparent chaos, Pluto's orbit remains stable over extensive timescales, such as billions of years. This implies that despite the seeming unpredictability of Pluto's journey around the Sun, there is an underlying order to it. Predicting the movements of celestial bodies, especially those with irregular orbits like Pluto, is an enormous challenge. The inherent unpredictability of these systems means that long-term predictions are fraught with uncertainties. While mathematical models are invaluable in understanding and forecasting the future movements of celestial bodies, they also highlight the limitations of our predictive capabilities. These models depend heavily on the accuracy of the initial conditions, and even the smallest error can lead to vastly different outcomes. The chaotic nature of planetary orbits, such as Pluto's, serves as a reminder of the ever-changing, dynamic nature of the universe. While we have made incredible progress in understanding space, Pluto's case demonstrates how much there is still to discover. The gravitational effects of the giant planets on Pluto's orbit provide valuable insights into the broader workings of the solar system. They reveal how the positioning of each planet can have profound effects on the stability and trajectory of other bodies within the system. So why have prominent astrophysicists recently raised concerns about a potential collision between Pluto and Neptune? Despite all these forces working to keep the 2 planets from colliding, Neil deGrasse Tyson, a leading astrophysicist, offers a unique perspective on the mysteries of our solar system, particularly Pluto. Tyson, who played a role in Pluto's reclassification as a dwarf planet, offers valuable insights into the evolving understanding of celestial mechanics and the public's renewed interest in overlooked aspects of space. Tyson views the renaming of Pluto as not a demotion but an essential adjustment in response to the expanding knowledge of the diverse objects orbiting the Sun. He believes that the complexities of orbits like Pluto reflect how much is still left to explore in space. The ongoing fascination with these questions fuels the excitement of space exploration. Despite Tyson's optimism, his concerns about Pluto's potential crash with Neptune suggest that there are still many unknowns regarding Pluto's orbit. Will Pluto collide with Neptune? Or is this just another instance of confusion in the ever-changing cosmos? Only time and further investigation will provide an answer. For now, we are left with an increased curiosity about how little we still know about our own solar system. We continue to study these celestial phenomena with the aim of uncovering the secrets that lie beyond. The possibility of a Pluto-Neptune impact raises further questions about the mysterious and fascinating universe in which we live. The prospect of an impact between Pluto and Neptune challenges our conventional understanding of planetary stability, especially considering the current relative strength of their orbits. Given Pluto's location on the outer edges of the solar system, far from the major planets, and Neptune's status as a gas giant with a powerful gravitational field, the implications of such an impact would be significant for our understanding of gravitational interactions and the solar system's evolution. To comprehend the dynamics of a potential collision, one must first consider the composition and properties of Pluto and Neptune. Pluto, despite being a dwarf planet, is composed of various substances that are believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered with nitrogen ice, and its atmosphere consists mainly of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a massive gas planet, is made primarily of hydrogen, helium, and other lighter elements with a dense, deep atmosphere. A collision between these vastly different bodies would alter their structure and behavior significantly, potentially creating an event visible across vast distances. What makes this hypothetical impact particularly intriguing is the influence of other bodies in the solar system. While Neptune's gravity plays a key role in stabilizing Pluto's orbit, it is not the only factor at play. Jupiter, with its immense mass and powerful gravitational pull, also has a stabilizing effect on Pluto's orbit, preventing it from drifting too close to Neptune. Saturn's gravitational influence further complicates the dynamics of the outer solar system, making a catastrophic event between Pluto and Neptune highly unlikely. However, despite the apparent risks, ongoing research has shown that the relationship between Pluto and Neptune is far more complex than a straightforward collision course. The gravitational resonance between Pluto and Neptune, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3, creates a cosmic lock that keeps them from directly colliding. This resonance is a critical factor in ensuring that Pluto and Neptune's orbits, while they intersect in the vastness of space, have never resulted in a direct collision. As we continue to explore the dynamics of Pluto's orbit, it's important to acknowledge that the relationship between Pluto and Neptune is not only a scientific curiosity but also a valuable tool for understanding the broader mechanisms that govern the entire solar system. Pluto's position at the outskirts of the solar system makes it an excellent example of how the gravitational interactions between distant bodies can maintain stability despite seemingly chaotic orbital paths. The complex balance of forces at play reveals just how finely tuned the solar system is, with even small changes having the potential to trigger cascading effects throughout the entire system. One of the fascinating aspects of Pluto's orbit is how it intersects Neptune's path in a way that might seem ripe for collision. Yet, instead of a catastrophic impact, the orbits of Pluto and Neptune are in what scientists call a resonant orbit. This means that their movements are synchronized in such a way that they avoid direct contact. This resonance, where Pluto completes 2 orbits for every 3 Neptune orbits, ensures that the 2 celestial bodies are never at the same point in their paths at the same time, even though their orbits cross. This delicate cosmic dance between the 2 objects is an incredible example of how gravitational interactions can create order out of what would otherwise seem like chaotic orbits. This resonance between Pluto and Neptune is just one example of the many ways that gravitational forces in the solar system work together to maintain stability. The gravitational pull of Jupiter, for instance, is so immense that it serves as a sort of guardian for the outer planets, including Pluto. By exerting a stabilizing influence on Pluto's orbit, Jupiter helps prevent the dwarf planet from straying too far into Neptune's territory. Similarly, Saturn's gravity contributes to the overall stability of the outer solar system, ensuring that bodies like Pluto maintain their relatively predictable orbits. Interestingly, even though the current arrangement of planetary orbits is stable, the solar system is not static. Over time, the positions and motions of the planets can shift due to gravitational interactions with other stars, the migration of planets, or other celestial events. This means that the stability we observe today is not guaranteed in the distant future. In fact, The orbits of some planets and other bodies in the solar system have changed significantly over the course of billions of years, and they will continue to do so. The study of these movements is a key area of research in astrophysics, as understanding these long-term changes helps scientists predict future events and learn more about the history of our solar system. While the gravitational forces at play in the outer solar system prevent Pluto and Neptune from colliding, there are other potential risks that could arise in the future. For example, interactions with passing stars or the influence of rogue planets could alter the orbits of Pluto and other objects in the Kuiper belt. Similarly, the gradual loss of mass from the Sun over time could have long-term effects on the orbits of the planets. As the Sun ages, it will eventually expand into a red giant, which could cause the inner planets to migrate outward and potentially destabilize the orbits of the outer planets, including Neptune and Pluto. Furthermore, the study of Pluto's orbit provides insights into the nature of dwarf planets and other small celestial bodies that populate the outer regions of our solar system. These objects, like Pluto, are often overlooked in favor of the larger planets, but they play a crucial role in helping scientists understand the processes that shaped the early solar system. The Kuiper belt, where Pluto resides, is home to countless other icy bodies and dwarf planets, each of which holds clues about the formation and evolution of the solar system. Studying Pluto and its interactions with Neptune allows scientists to infer how the solar system might have looked billions of years ago and how it continues to evolve. Additionally, the potential for a Pluto-Neptune collision, while highly unlikely, raises important questions about the stability of other planetary systems. Could other solar systems have planets with similar orbital configurations? How might the interactions between those planets evolve over time? By studying Pluto's orbit and its relationship with Neptune, scientists gain a better understanding of the complex gravitational interactions that occur in other star systems, which could help inform our search for potentially habitable planets in distant solar systems. In conclusion, the possibility of a Pluto-Neptune collision, while currently improbable, offers valuable insights into the intricate nature of our solar system. Through careful study of these distant objects, we can better understand the forces that govern our solar system and the universe at large. The complex interplay of gravitational forces, orbital resonances, and the role of other planets in stabilizing orbits highlights the delicate balance that exists in space. As our knowledge of these celestial phenomena continues to grow, so too will our understanding of the vast, dynamic, and ever-evolving cosmos.